Okay, guys, I guess we are all set to start with one of the most interesting chapters of mechanics. Many people love this chapter. There's a high percent of teachers as well as students who love this chapter. Hopefully, you are also going to love it. And the key to that would be understanding the equation F is equal to ma, which is at the heart of the chapter. So no fancy things are happening, like speeds near to light is not happening, masses which are very very small and to the atomic level is not happening. These are normal speeds, normal masses, and we have to understand this equation very well and then start applying the equation on the various situations given to you: block, pulley, wedge, different systems. So what does this equation say? The equation tells you that if there is a body and there is a net external force on the body, net external force, that means vector addition of all the forces applied on the body. Various forces are applied on the body. All of these forces will have one net direction, all these forces totally will result in one force, that is your F external force. So let me put this in blue and draw the force with the vector addition of all them. Like you used to draw, take one, and then on the head of that you put the tail of the another one, and then this one maybe, and then that one maybe, and then the next one, then this one I put, then this one I put, and ultimately I am getting that the force, net external force, is this way, suppose. So if the net external force is this way, then the body is going to go this way. The mass m is going to go this way. That is the direction of the force and the direction of the acceleration. Now, going to go is not that good statement to make. It is going to accelerate this way. It is good. The acceleration is going to be that way. Now, the body, if it was moving in some other direction initially and it was not at rest, then maybe it was having a motion this way. Some velocity was that way. Then it is going to accelerate that way, means the velocity is going to turn this way. The velocity is going to turn a bit, and try to align with the acceleration over a period of time. So again, not going into that also. If the body was at rest and the net external force happens to be in this direction, then the acceleration will be in that direction. And what would be the magnitude of the acceleration? The magnitude of the acceleration, your acceleration, would be equal to the applied force divided by the mass of the body. So if the net force was, say, 10 Newton this way, if the net force was 10 Newton this way, if it's a 10 kg body, then it is going to give a certain acceleration, which is 10 divided by 10, 1 meter per second square. But if it is a 1 kg body, it is going to give a lot of acceleration, 10 divided by 1, which is 10 meter per second square. So it depends how massive the body was, how much of inertia the body had, and dependent on the force, dependent on the mass, will be your acceleration. So the left hand side of the equation will be all the forces added, and the right hand side of the equation would be the acceleration. Now what I would like to emphasize over here, that the quantity m times a is not a force, is not a force. Remember this. F is proportional to A and F is proportional to the mass. So ultimately what you get is F is equal to mass times acceleration, and the constant of proportionality has been taken as 1 by Newton, defining the units of force as Newton. So that makes things simple when we are solving it. So had it been some other unit, there could have been some other constant of proportionality, by the way. Hence you can very well imagine, suppose the constant of proportionality was 2. This 2ma is not a force. Ma is not a force. Ma is not a force is what I am repeating again and again. The equation says that F is mass times acceleration. It doesn't mean that force is mass into acceleration. Force is not mass into acceleration. Force is force, acceleration is acceleration, mass is mass. So don't confuse ma as a force. It's a relation between force, mass and acceleration. Okay guys, let's investigate or talk about this F is equal to ma a bit more before we go on to the problems. Now as I told you, F is the total net external force on a body. So suppose the net external force on the body comes to be in this direction. That's your F. And the body is actually moving. The acceleration happens to be in this direction. That is your acceleration A. Now how is that possible? Maybe there was a platform and this platform was moving down while the body was going forward or whatever. The acceleration with respect to ground is this direction, the red direction, and the force is orange direction. Now how to deal with such questions? There are two ways of dealing with it. There are many ways of dealing with it. Two recommended ways. One is break the force into two components which are 90 degree to each other. Why do we break forces which are 90 degree to each other? Let me show you over here. Why do we do that? There's a certain mass M and you have a force F vertical and a force F horizontal. Now suppose I know for sure that the body is going forward with a certain acceleration A, because there was a platform which it cannot go through, so the body was going forward. Now who is responsible for this acceleration? This force, this vertical force, has got zero responsibility for this A acceleration. This vertical force has no tendency to move the mass forward or backwards. It has got nothing to do with the horizontal acceleration. So the vertical force Fy was not responsible for the acceleration A at all. Who is causing this acceleration A? What is causing this acceleration A? The acceleration A is caused due to the horizontal forces. Whatever horizontal force is there. Fx is a horizontal force. Maybe there is a friction over here, which is a horizontal force. All those forces will cause acceleration A. So Fx, let Fx is the only horizontal force. Then over here, Fx will be responsible for the acceleration in the horizontal direction, and the relation will be given by F is equal to ma. So A precisely over here is just the horizontal acceleration. So what we see over here is a 90 degree force doesn't have any effect on the motion. The force which is 90 degree to the direction of motion in study has got no effect in that direction. So if I break this vector in two components which are 90 degree to each other, those two components are not going to interfere with each other. This F will have no support for Fx, neither it is going to oppose it. Had we broken the vector, we can very well break vectors in any given direction we want. The components of the vector can be, let me just make in blue, these are the components of the vector. I call this as Fx vector and some F dash vector. Is Fx plus F dash equal to the net force F? Yes, it is equal to. Are they the components? Yes, they are the components. But is it a good way to resolve them? Not at all, because this F dash itself will have an effect in the x direction. The F dash itself will have a horizontal component as well as a vertical component. So F dash is having an effect on Fx, it is getting added to Fx, so they are not independent totally. Hence any study in this direction will have an effect of F dash also and Fx also. So that's not a good way of breaking a force. So the good way of breaking the force is any direction and 90 degree to that direction. Any direction, by any direction I mean, if you have a force like this, I can have a component in this direction, because that was the requirement for the timing, like this one. This comes exactly in that line, so say this one. So the force can be broken 90 degree to the direction and along the direction. If I box up the force, then the force which has to be broken, I hope you know, is the diagonal of the parallelogram, and if you are breaking it into 90 degrees, then it is the diagonal of a rectangle. So you can box it up. The diagonal is the actual force, and these are the two components. You can call one as Fx and the other one as Fy. So Fx and Fy need not be like vertical and horizontal in the way you are looking at it. So it is any two direction but 90 degree to each other. That's the best way of breaking. So that is the only way of breaking in this chapter. Do not break in components which are not 90 degree to each other. It won't be of any use. It won't be of much use. So here I can break the force. So I will do away with this force in fx direction, I hope you know how much is fx. Fx will be f cos theta, and in the y direction, I'll call that much force as Fy, that will be f sine theta. So instead of f, so now this f is gone. Instead of f, I have Fy and Fx. We don't have all three. I've cancelled out this one. Now this force is gone. There's no more this force. These two are equivalent to that. These two can be considered as two independent forces on their own. Now Fx will cause the acceleration in the x direction and Fy will cause the acceleration in the y direction, but the guy is neither moving in the x direction nor in the y direction. It is moving in some other angle, so maybe that angle is, say, phi. Now what we can do is we can break the acceleration. It is also a vector. Acceleration also being a vector, we can break it into two directions, which is horizontal and vertical. So in the horizontal, I'll call it as ax, which from the diagram you can see is a cos theta, and the vertical as ay, which is a sine theta. So what we have over here is we have a body which has two forces acting, Fy and Fx, and it is having acceleration in a slant way, which has been broken into two components, ax and ay. What we can safely say that this ax was the total responsibility of Fx. Fy had got nothing to do with it. So your Fx and Ax will be related by this equation, which is Fx is equal to mass times the acceleration. And the vertical component is the only guy responsible for the vertical acceleration, which is in the equation form given as Fy is equal to mass times acceleration in the vertical direction. So breaking the components in the two directions, we can get the acceleration in the two directions. Neither of the two accelerations, neither this nor this, is the actual acceleration. Actual acceleration is that which can be later on we can get that by adding the two vectors, and don't worry, both are at 90 degrees, so the addition is quite simple. It is the value of that square plus the value of ay square whole under root will be the value of this, and the direction will be given by, you can figure out this phi, sorry, this was phi over there, that's phi, I'm very sorry, theta is over there, so make that correction. So the angle you can find out by dividing ay with ax and call that angle as tan phi, so you can have the tan phi. So this is one way. Now the other way of dealing with the same situation was your body is going in that way at an angle phi, which is maybe known, maybe unknown, and you had a force in this direction F at an angle theta. Now if you know that the body is going in that way, if you know the direction, then it would be best to resolve this force in two directions. One is along the acceleration and the other one is 90 degree to the acceleration. So I've already shown it over there, I think. Yeah, it is there. So your Fx along the direction of acceleration and Fy, this is not the same Fx and Fy what was over there. I'll write as f dash x, f dash y. And which is Fy, which is 90 degree to the direction. So what happens over here is Fy is not responsible for any acceleration. The body is not going in this direction at all. So Fy is not responsible for a motion in that direction. So what we'll have over here is your Fx dash, which is the forward direction thing, is the only guy which is responsible for the acceleration, which is a in that direction. Now how to get that Fx? Now to get that Fx, we'll have to find this angle. This angle is not theta now, by the way, I'll call it as theta dash. Your theta was this much. That was your theta. So over here, this is your phi. So this is your vertically opposite angle, this one. That's your phi. This is also your phi. So how much is this theta dash? Your theta dash will be theta minus phi. So theta dash is theta minus phi. So this f dash x would be equal to F times cos of theta minus phi in this case. So you'll have maybe a bit of trigonometry to do when you're solving in this way. So whether you do this way or that way, your ultimate answer is going to be same. In terms of trigonometric expression, it might look a bit different, but then your strength of trigonometry is going to play a role over there. You'll have to convert from one form to the other form. The answer would be the same numerically. So the expression might look different. So the point over here is, we have to, if we have a mass and we know the direction of acceleration and we have a force not in that direction, we have to break the force in two components which are 90 degree to each other. The force components are 90 degree to each other, such that one of the component is along the acceleration and the other one is 90 degree to the acceleration. That would be the best scenario. So if this is not possible, then if acceleration is in some other direction, we'll break the acceleration also in the two directions as the two directions of the forces, but always the breaking of the forces or the acceleration will be in a certain line and 90 degree to that line. And what is that line? According to the question, the most convenient, like along a slide or something, along a platform or something, the most convenient direction. That is, that would be our aim. Many a times we have more than one option, and and both the options are equally short or long. So that is this point. Force in a direction is not responsible for acceleration perpendicular to the direction of force. So you will break in a direction perpendicular to the direction of motion and along the direction of motion. Now the next important point on this F external is equal to mass time acceleration is to pay some emphasis